Hello students, welcome to the digital learning of session 8 of unit groups of BSc 3rd Sem Mathematics. I am Dr. Shashikala. In this session 8, let us discuss about Lagrange's theorem and examples on Lagrange's theorem.
Lagrange's theorem. The statement of the Lagrange's theorem is the order of a subgroup of a finite group G is a divisor of the order of the group G. That is, we have to prove it that order of H divides order of G. So, if H is a subgroup of the finite group G. So, you have to remember this Lagrange's theorem, and proving is also important. Proof. Let the order of the finite group G is equal to n there, and let H be the subgroup of the G where order of the H is m. So consider the right coset to prove this, or you can also consider the left cosets. Right coset or left coset, any of the coset we can consider. If we are considering for right cosets, so it becomes HA. So set of the HA is H1A, H2A, H3A up to the HM of A, where H is taken as H1, H2, H3 up to the HM, and A belongs to G here. Now all the elements of HA are distinct. That means H1 of A is different from H2 of A, is different from the H3 of A. So here we have to remember, or we have to concentrate on the distinct elements. See, we are telling that HA elements of the HA are distinct. That means they are different. They are not same. H1 of A is different from H2 of A. H2 of A is different from H3 of A. So every element is different here. So if we are taking the contradiction of this, that is Hi of A is equal to H2 of A. That is, if H1 of A is equal to H2 of A, what happens? Let us see. Taking the operation A inverse on both the sides. So we got it Hi into A inverse, which is equal to HA of A inverse. So A inverse becomes the E here. So Hi E equal to HA into E, because so we got it as A inverse. In right hand side also we got it A inverse. A inverse becomes the E. Therefore, we have HIE is equal to HAE. So identity element with HI is taking as HI only. So identity element with HA is taking as HJ. See, if you are observing here, HI is equal to HA. So what we wanted, we wanted HI is not equal to HA, because we are telling that these two are distinct elements, these two are different elements. But by our contradiction, we got it as HI equal to HA. Therefore, which is not true. What we have taken initially is not true. So therefore, since all the elements in HA are distinct, so that means whatever we have taken is wrong here. So what we supposed to take is the element H is a distinct. So distinct is fixed here. We proved it. Since the group is finite, then number of such right cosets will be finite. That means we consider right cosets here, and it's a finite right cosets elements we consider. Let the number of distinct right cosets be K. So how many right cosets we have taken? The number of distinct right cosets is taking as a K there. So let's take a union of all these right distinct cosets. So that is HA1 union HA2 union HA3. Let us take all this as a equal to G. Then each coset is having m elements. HA1 is having a m elements, HA2 is having a m elements, like this. All the cosets is having a m elements. but G is having a n elements here. So order of G is equal to n. So coset, right coset is having a m element. The group G is having a n element here. So order of G is equal to n. Therefore, so we can write it as n is equal to m times of the K. So by the congruent, the property. So remember that we are taking the Lagranges. That is, we have to prove it for order of H divides the order of G. So here order of G is equal to n and order of H is equal to m here. So n is equal to, taking n is equal to mk. So m is the congruent property. By the congruent property we can say that m divides the n. M divides the n here. So order of H divides the order of G. Thus the order of the subgroup H divides the order of the group G here. So Lagrange's theorem is proved. Based on the Lagrange's theorem, let us prove it the theorem. Let G be a finite group for all A belongs to G, then prove that A to the power order of G is equal to E. So let us take the group as a G here, which is a finite one. Then let A belongs to G and order of A is equal to m here and order of G is equal to n. That is, it's like order of H, the subgroup we are considering as a order of A here, that we are naming as a m. By the definition, let us take A power m is equal to E. So A power m, we can take it in the form of A power n. So that is usually the cyclic group is taking as a power n. So here we can also take it as a power m, which is equal to E here. Since order of A divides the order of G, this is by what? This is by the Lagrange's theorem. So order of A divides the order of G. So order of A is taken as m, order of G is taken as a n. Therefore, m divides the n. So we can write it as n equal to m into k by the congruent property. So taking A power m equal to E, taking qth root on both the sides, we got it as A power mq equal to E power q is taken as just a E. So mq is mentioning as n here, A power n is equal to E. So n is what? N is taken as, initially we have taken n as an order of G. Therefore, A to the power order of G equal to E here. Nextly, go for examples on the cosets. If G is equal to 1 minus 1 I minus I under the operation multiplication be a group and H is equal to minus 1 and 1 be a subgroup of G, then write all the right coset of H in G. See, in previous examples we have seen how the number of right cosets we can find out. By the Lagrange's theorem, easily we can find out the number of right cosets. So let order of G is equal to 4, then order of H is equal to 2. So from the group G, the elements are 4. Then from the H, the subgroup H, the elements are 2 here. Order of G is equal to 4 and order of H is equal to 2. By the Lagrange's theorem, we have the formula order of H divides the order of G. So we can write it as order of G is equal to K times of the order of H. So K is equal to what? Order of G divided by the order of H. So order of H value is 4 here, which is divided by the order of H. Order of H is 2. Therefore 4 is divided by 2. So K value is 2 here. That is, the number of right cosets are 2 here. So we have already seen what are the right cosets. It is a 1 and minus 1. So coset means what? It is a distinct elements. So it is a disjoint elements are. Disjoint sets we can consider as a right coset. Disjoint cosets are 1 and minus 1 and I and minus I. So therefore these are the two right cosets. So So therefore number of right cosets are 2 here. Find all the left cosets of the subgroup H is equal to 0, 4, 8 in Z12 under the addition modulo 12. See, order of H is 3 here, then order of G is 12. Because why the order of G is 12? Because it is under the addition modulo 12. So easily we can find out by the Lagrange's theorem. Lagrange's theorem says that order of H divides the order of G. Order of H is what? Order of H is 3. Order of G is 12. Again, we can take it as order of G equal to K times the order of H. So K is equal to order of H divided by order of H. So order of G is how much? Order of G is 12. Order of H is 3. So 12 divided by 3 is 4. Then, so we have to find out for our left cosets. These are the K is equal to 4 means it is a number of cosets. So let us go for number of left cosets. So it is in the form of A into H. So 0 addition modulo 12 of H is equal to 0, 4, 8. How we are getting? So it is a 0. It is a 0. H is in the place of H we can consider 0 firstly. Therefore 0 plus 0 becomes 0. Then 0 addition modulo 12 of. Addition modulo 12 means 0 plus 4 becomes a 4. Then 0 plus 8 becomes a 8. So all these values are under the 12 only. Therefore directly we can write it like this. Then take a next element 1. So 1 plus H. H values are 0, 4, 8. 1 plus 0 is 1. 1 plus 4 is 5. 1 plus 8 becomes a 9. All these values are under the 12 only. Nextly for 2 addition modulo 12 of H. So 2 plus 0, 2. 2 plus 4 becomes a 6. 2 plus 8 becomes a 10. So all these values again under the 12 only. Then 3 plus H is 0. 3 plus 0 is 3. 3 plus 4 becomes the 7. Then 3 plus 8 becomes the 11. So all these values again under the 12 only. So if you are observing all these values so are below the 11 only. So therefore see from 0 to 11 we got it the values. So therefore Z12 is from 0 to 11. Nextly go for one more example. If G is a cyclic group of order 9 generated by A, find the subgroup generated by A. Since G is a cyclic group of order 9, they have already given, and generated by A they have said. So since it is a cyclic group, we have to write it G as a power n, where n is integer and A belongs to the group. So since it is in the power form, so and order 9, so it starts from A power 1 to the A power 9. So order of G is what? Order of G is 9 here, then order of A is also 9. Therefore, the generator of G are, so here it is a 9. Order of G is a 9 and order of A is also 9. So we can consider the generator as 1, 3 and 9. So nextly subgroup of G are the only subgroup generated by, so we have to consider in the form of the power A power n. So the generator of G is 1, 3, 9. Therefore the subgroup of G has to be written in the form of A to the power 1, A to the power 3, A to the power 9. Therefore, so again the subgroup generated by A cube is given by again A cube to the power 1, A cube to the power 2, A cube to the power 3 is finally written as A cube, A to the power 6 and A to the power 9 like this. So we have to find out the subgroup generated by A. Let us go for the next example. Find all the right cosets and the left cosets of the group. H is 0, 3, 6, 9 of the integer 12 of the operation, the addition modulo 12. So set 12, frame the set here from 0 to 11. Therefore order of set 12 is 12 here. Then h is 0, 3, 6, 9. Therefore order of h is 4. Firstly, to find out the number of cosets, order of Z12 is 12, then order of H is 4 here. So order of G is 12 here, order of H is 4, therefore number of cosets will be 3. Nextly, to find out for the right coset, so H into A form, right coset H into A form, therefore in the place of H we can replace the values of 0, 3, 6 and the 9. 0 plus 0 becomes 0, then 3 plus 0 becomes 3, then 6 plus 0 becomes the 6, then 9 plus 0 becomes the 9. Similarly, h plus 1. So h values are 0, 3, 6 and 9. 0 plus 1 becomes the 1, 3 plus 1 becomes the 4, 6 plus 1 becomes the 7 and 9 plus 1 becomes the 10. So all these values are under the 12 only. Then again h values are 0, 3, 6, 9. So 0 plus 2, 2, 3 plus 2, 5, 6 plus 2, 8, then 9 plus 2 becomes the 11. All these values again under the 12 only. To find out the left cosets, again here it is in the form of A into H. Again similarly as we have seen in the right cosets, values of H are replaced by 0, 3, 6 and 9. So therefore we got these values. So if you are observing the right cosets, the values and the left cosets values, these are similar. Therefore number of left cosets order is equal to the number of right cosets. Therefore the Lagrange's theorem is proved here.